Okay, let's unpack this. Have you ever, looked at a triangle and just wondered about the basic rules? Like, why does the pointy bit have the long side opposite?
Uh-huh. Or why can't you just slap any three lengths together and call it a triangle?
Exactly. So today, we're doing a deep dive. We've got this stack of source material all about inequalities in geometry, mostly triangles.
Right.
And our mission really is to just pull out the key stuff, the essential rules, get a quick handle on how triangle sides and angles relate.
And it's more than just theory, isn't it? These rules pop up everywhere.
Yeah.
Building things, measuring stuff.
Oh, definitely. Stability in bridges, navigation.
Yeah, or just understanding why shapes are the way they are.
Yeah.
The material lays out these theorems that basically connect bigger than or smaller than to actual triangle properties.
Okay, so where does the source material start? What's the first big idea?
Well, it kicks off with what feels like the most fundamental side length versus the angle opposite it.
Makes sense.
The core idea presented is, if you've got two sides of a triangle and they're not equal, the angle across from the longer side, that angle's always bigger.
And that just feels right, doesn't it? Like intuitively, a wider angle needs more space across from it.
It does. And the flip side is also true. If you have two angles that are unequal, the side opposite the bigger angle is always the longer side.
Okay, so it works both ways. Angle size dictates opposite side length.
Yeah.
The side length dictates opposite angle size.
Exactly. And proving that second part often leans on the first one, and crucially, on the triangle inequality.
Ah, yes. The triangle inequality. I feel like that's one people might have heard of. The source calls it a corollary.
Yeah, it sort of builds from those basic ideas. The main takeaway, the absolute must-know part, is this. Pick any two sides of a triangle. Their lengths added together must be greater than the length of the third side. Always.
Right, because if they weren't, they just wouldn't reach. You couldn't connect them to make the third corner.
You literally couldn't form the triangle. It's like a basic entry requirement for being a triangle in, flat space.
Got it. Like trying to bridge a wide river with two planks that are too short.
Precisely. And the material adds a related point. The difference between any two sides is always less than the third side.
Okay, so the third side is kind of trapped lengthwise between the sum and the difference of the other two.
That's a good way to put it. It's bounded.
So we've got side angle connection and these rules about adding and subtracting sides. What else? The source mentioned something about shortest distances.
Ah, yes. From a point to a line, it proves pretty definitively that the shortest path from some point not on a line down to that line, well, it's always the perpendicular
A
segment.
straight down path, basically.
Right. And the logic actually loops back to that side angle rule. In the right triangle form, the right angle, 90 degrees, is the biggest angle. So the side opposite it, the hypotenuse, which is any other line from the point to the line, has to be longer than the perpendicular side, which is opposite a smaller acute angle.
That's neat. Using the triangle rules to prove something about points and lines. Okay, so the material builds on these basics.
It does. It gets into some less obvious properties, like one showing the sum of two sides of a triangle is greater than twice the median drawn to the third side.
Wait, say that again? The length around two sides is connected to a line inside the triangle, the median.
Yeah, the line from a corner to the midpoint of the opposite side. It's not immediately obvious, is it?
No.
But if you apply the triangle inequality cleverly to the smaller triangles the median creates, it just falls out. And then building on that,
Okay.
it shows the whole perimeter, all three sides added up, is always bigger than the sum of all three medians.
Whoa. Okay, that is surprising. The distance all the way around is more than those three internal lines added together.
It really shows how these simple rules stack up, Another example. Take any point P inside a triangle.
Okay.
The distance from P to two corners, say PA plus PB, that sum is less than the sum of the two actual triangle sides that meet at the third corner, like AC plus BC.
Huh. So being inside makes the path shorter in that sense.
And again, it comes directly from using the triangle inequality multiple times.
Right. So let's recap. We've looked at how sides and opposite angles are linked, the absolute must-have triangle inequality for side lengths, both sums and differences, why the shortest distance to a line is the perpendicular.
And then these cool results about medians, like the perimeter being greater than their sum.
Yeah. So what's the big picture here? It seems like all these, fairly simple foundational rules, they combine in ways that let you prove some powerful, sometimes kind of unexpected things about shapes, right? About the space they exist in. Think about that, how basic definitions can build up to reveal these deeper geometric truths.